Further, if we talk about the combination of resistor, so you know that there are two types of combination. One is series and other one is parallel combination, right?
Yes.
So we have two types of combination. One is series combination and the second one is parallel combination. And when we are talking about series combination, so series combination means we need to connect resistors connect resistors end by end. We already discussed the concept that we need to connect one end of one resistor to the second end of second resistor, then the second end of second resistor connected with the first end of third resistor and so on. So it will be like a series, one by one, one, two, three, four. And if you know about the symbol of the resistor, so the symbol diagram is like this for resistor. So this is R1 and we connect one resistor on right. So this will be R2, then R3. So this combination is for series combination, end by end connection, right?
Yeah.
And if we talk about parallel combination, so parallel combination means we need to connect resistor by same ends. Connect resistors by same ends. So it means that we need to connect first end of the resistor on a single side. Then we need to connect the other end of the resistor on the next side. So let's suppose we are going to connect three resistors. So these are three resistors which are connected by same ends, and then it will connected with a power source over here. So there are two types of combination in resistor. So when we are talking about series combination, so what is the advantage of using series combination? What is the advantage of using parallel combination? So let's suppose if we first continue with the parallel combination. So let's suppose if we have two or more than two resistors, and let's suppose all values of resistors are greater. Let's suppose 10 ohm, 20 ohm, 5 ohms, but we need a small resistor, right? Like less than 5 ohm resistance. Let's suppose, for example, we have three resistors, 5 ohms, 10 ohms, and 15 ohms. We are having three resistors of different values. All values are greater. And let's suppose we need a small resistor. It means less than 5 ohm. We need to connect a resistor in our circuit which is less than 5 ohm. And we need to combine all these three resistors. So there are two possibilities. Either we connect them in series or either we connect them in parallel. But we don't know if we combine them in series or if we combine them in parallel. So what will be the output, right? So for that purpose, we need to first find out what will be the output of parallel combination. So when we are talking about parallel combination, so the output of parallel combination will be like 1 over R is equals to 1 over R1 plus 1 over R2 plus 1 over R3. So this is the combination of parallel resistors, right?
Yes.
And if we talk about the conclusion, what is the conclusion of connecting resistors in parallel combination? So conclusion will be like this. If you combine all these values, 1 over 5 plus 1 over 10 plus 1 over 15, so you will definitely get a low value resistor that it will be less than 5 ohms, right? So if you want to write the conclusion, so conclusion for the parallel combination will be like this. So in exam, you know that they ask with the reference of equivalent resistance, final resistance, total resistance. So this R basically represents you the equivalent resistance. So we may write it as equivalent resistance in parallel combination in parallel combination will be equal to the sum of reciprocal of individual resistance, right? Will be equal to the reciprocal So when we are going to talk about the equivalent resistance in parallel combination, so equivalent resistance in parallel combination will be equal to the sum of reciprocal. So we need to add over here sum of reciprocal of all resistance, right? And one more thing, which is important over here, that if you find out the equivalent resistance, so that equivalent resistance will be, so equivalent resistance will be less than individual resistance, right?
Yes.
It means that if you find out the resistance by using the values which we already suppose for parallel combination, so your answer will be less than 5 ohms, right? Let's suppose in some question you are going to calculate the final resistance or equivalent resistance in parallel combination, and let's suppose that these three values are given 5 ohm, 10 ohm, 15 ohms, and your answer will be like 7 or 8 ohms. So that answer will not be correct because we know in parallel combination your answer or equivalent resistance will be less than individual one, right? So it must be less than 5 ohm if we are using these values, or if we are using some other values. So equivalent resistance will be less than the smallest value uh, in your given data, right?
Yes.
Okay. So in series combination, the second combination. So if we are talking about the relation for the series combination, so relation is simple. You just need to add up all resistance R1 plus R2 plus R3. So that will be equal to the combination of all resistors, just simple like the speed breaker. Because we know that in series combination resistance will be high, right? Because current will pass through a single line, and when the current is passing through a single line, so if we connect more than two resistors over there, so it means their resistance will automatically add up just like the speed breaker on a road in a straight line, right?
Yes.
And for the conclusion, let's suppose if we add up all these three values over here again, so we will get a greater answer that will be greater than the individual resistance, which is 15 ohm, because 15 is the greatest value in our given data. So our equivalent resistance or final resistance in series combination will be greater than 15 ohms, right? So
Yes.
for conclusion, we may write it as that equivalent resistance will be greater than the individual resistance, right? So that is the identification for this, greater than the individual resistance. And conclusion will be like this, that equivalent resistance in series combination, equivalent resistance in series combination will be equal to what?
The sum of all resistance?
Yes, the sum of all resistance will be equal to the sum of all resistance, right? So these are some concepts related to the combination of resistors, right?
Yes.
And you already know that how to use the formula of resistance. We already solved in the questions. Further, if we talk about the topics in this chapter, so topics are like energy and power, that how to calculate the energy, how to calculate the power. So any confusion in that?
No, that's okay.
Because those are simple formula and you know that how to convert into kilowatt hour, how to change value, what are the formula for energy and power. So I think there will be no confusion, right?
Yes.
Okay. Okay, so let's move towards electromagnetism, right?
Okay, sir.
And in electromagnetism, starting from the first concept. So the very first concept is related to So if we start talking about electromagnetism, so first of all, let's suppose consider a simple case. Let's suppose there is a wire or a conductor and current is passing through the conductor or a wire. So we know that charges are moving through that. We already studied in electricity that the moving charges or rate of flow of charges is known as electric current. So when charges are moving through the conductor or the wire, so that will give you the concept of electric current. But there is something special over there when current is passing through the conductor. So one more thing over there is that magnetic field will also generate around the around conductor when current is passing through the conductor, right? So when we talk about the very first concept in electromagnetism, so the very first concept related to electromagnetism is we know that we are going to work with electricity and magnetism combined. In the concept of magnetism, you know about the basic quantities that north and north, it means same poles will repel each other, unlike poles will attract each other. And further, we know the basic phenomena of magnetism. I think there will be no confusion because most of the part is now excluded from our syllabus. So we don't need to discuss very much in detail about magnetism. You will get all idea in the chapter of electromagnetism, right?
Yes.
So the first concept in this chapter is that you need to know about the magnetic field around a current carrying conductor. So magnetic field around a current carrying conductor. Okay, so when we are talking about the magnetic field around a current carrying conductor, so let's suppose we consider a straight wire over here, and current is passing in upward direction. So this is the direction of electric current passing through the wire or through the conductor. So if you need to find out the direction of magnetic field, so how we can find out the direction?
The left hand rule?
Left hand rule or right hand rule for this concept? Okay, for
Oh, right.
yes, when you just need to find out the direction of magnetic field when current is passing through the conductor, so you just need to use a right hand rule, right?
Oh,
So
right there.
you need to place a thumb in the direction of electric current. If current is moving through a straight wire or through a straight conductor, so we need to place thumb in the direction of electric current. So basically thumb represents the direction of electric current, and your curl of the finger gives you the combination of magnetic field. So fingers will give you the concept of magnetic field around the conductor. So the direction of magnetic field will be clockwise or anti-clockwise in this situation.
Anti-clockwise?
Okay, so it will be like this, and that is anti-clockwise, right? And if we reverse the direction of electric current, so the direction of magnetic field will also automatically reverse, right? So you just need to use a right hand rule. Place any pencil pen in your palm and just place it in the direction of your thumb. So that will give you the direction of electric current. So suppose that current is passing through the conductor like this, and your curl of finger gives you the concept of magnetic field, right?
Yes.
So in this particular case, current is moving in upward direction, and for magnetic field, we are getting direction anti-clockwise. So this is the first concept. You need to use this right hand rule when you just need to find out the direction of magnetic field by using a current through conductor, right? There is no force included over there. There are only two quantities which we are talking about in this particular case, right? And let's suppose if the conductor is not a straight wire, let's suppose if conductor is a coil. So this is case number one. And let's suppose if we talk about the second case, when we are talking that current is moving through a coil. So let's suppose coil will be like this. and current is passing in upward direction from left hand side like this, and then current moves in a circular path through the wire and then ends up over here on right hand side in downward position. So now if you want to find out the direction of magnetic field in this situation, so what will be the direction of magnetic field? Now current is moving in circular form. What will next? Now we need to find out the direction of magnetic field.
So, sir, will we use the right hand rule?
Yes, again you need to use a right hand rule, but there is some difficulty over here that how we find out the direction of electric current, because electric current is moving in a circular path. So by using our thumb and by using the same concept of right hand rule we discussed in the first example, so that will be not enough to find out the direction of magnetic field because current is continuously changing its direction. Let's suppose if we consider this path, so current is moving in downward position and in upward position from the back of the coil, right? So now you need to place your hand like this. That will give you the exact direction of electric current is starting from the first end of the coil ending to the last end of the coil. So let's suppose if we consider this example. So in this particular example, our rotation will be like, now if you consider this first point, so current starts moving from this direction and current is moving in upward direction, right? And then this is the second point. So we consider starting 2 points from this coil, right? So first current is moving first in upward direction, then it is moving in downward direction, right? So now you need to use your finger curl to find out the direction of electric current. So these two direction can be identified with the help of your fingers now. Previously, we are finding the direction of current with the reference of thumb, but now we have to use that same right hand rule, but with different quantities. Now we need to use the finger curl for electric current because current in a circular form. So now you need to curl your fingers. So there are two possibilities. Let's suppose if we consider with the reference of screen. So one possibility is that palm is facing towards you, and the second possibility is palm is facing towards the screen, right?
Yes, sir.
So now you need to place your right hand in the case that current or your finger will curl or your palm is facing towards your side. So you need to first place your right hand in front of you. That palm is facing your side. And what next? You need to curl your fingers. So that will give you the exact direction of electric current with the reference of this coil. So you need to place your right hand rule first. So your fingers will be like this. That thumb will indicate in right hand side. So this is the direction of thumb, and this direction gives you the concept of electric current. So you need to place your hand like this, right? And when you curl your finger, so fingers are going to curl in your direction. Getting my point?
Yes. Sir, how do we know if we should curl it towards us or towards the screen?
So that is the question. So you need to first check out the exact direction of electric current. Let's suppose if we consider this specific example of coil. So first current is moving in upward direction. So you already know that first you need to place your hand like this, that finger will point in upward direction, right? Because current is first moving in upward direction. So when you place your hand, either palm is facing your side or palm is facing towards the screen. So in both condition, your fingers are in upward direction, right?
Yes.
Now the second question is, that after moving in upward direction, in which direction current is now moving, in downward position and some other position. So first current is moving in upward direction, so it ultimately move in downward direction because it bends towards through the coil. So you need to curl your finger like this, that will be facing towards, or your finger will move or curl in downward direction. So you need to place your hand like this. That finger is either current is moving downward direction in your front, or current is moving or current is bending in the backward direction. Because in this specific condition, we consider that this is the front side of the coil. If we consider this concept, so basically this gives you the front side of the coil, and this represents you the back side of the coil, right? I will show you a real picture of the coil, so that will give you a more clear concept for this. Just give me a minute. Okay, so in this specific diagram, you will get the idea of the direction of rotation of current in the coil, right? Screen is visible.
Yes, sir.
Okay, so now there are two different possibilities, that either current will start moving first in upward direction, or it will start moving from some other direction. So it depends upon the direction of current, that will also change the rotation of the current, right? Let's suppose in our case, we are talking about that current is moving in upward direction from left hand side. But in this diagram, current is moving in upward direction but from right hand side. So current starts moving in upward direction from this side. So it depends upon the direction of current. So let's suppose in this concept, current first move in upward direction. Now it is moving from the back of the conductor, right? So from back of the conductor, it will move in upward direction. But in front of conductor, because we need to identify the direction with the reference of the diagram, we are not going to perform real practical. So we can only identify the direction by the reference of the diagram given in the paper. So you need to place your hand in such a way that your fingers will represent, or your finger will curl in the same direction like electric current. So let's suppose, uh, for the time being, just ignore this hand, and you try to find out by yourself that what will be the direction of the North Pole. Because in this situation, gave you the concept of the direction of North Pole, right? Because there are two poles, but we have only one thumb in one hand, so we can only identify one direction, single direction, in one time. So we need to identify the North Pole, because we know that magnetic field will always flow from North to South Pole, right? So now just consider a pen or a pencil in your hand as a conductor, and let's consider, or let's try to solve with the same situation which is mentioned in the diagram, that current is moving in this way. It means in upward direction, but from the front of the coil to the back of the coil. So now first you need to place your palm in such condition that your finger will curl in the same direction. So in which manner you need to place your hand? Palm is facing towards the screen or front of you?
Towards screen?
Towards the screen, because when you place your hand towards the screen, so your finger will curl in backward direction, or we can say that in the back side of the screen, right?
Yes.
Any confusion now?
No, it's clear.
And if you reverse the direction,
Then towards us?
then towards us that we are talking in our example. So that is the concept. So there are two possibilities also. Let's suppose if we consider this hand now. So we consider that we are going to place our palm towards the screen and we curl the finger from the upper side. So our hand will be like this. So we cover the front part first, like this. Our fingers will be like this in the front of the coil, and our thumb will be like this, right? And let's suppose if you hold the conductor in some other manner, let's suppose palm is facing towards your side. So you need to curl your finger from the bottom of the conductor. So you will get the same concept, just like the example which is mentioned in the diagram over here. So in both concepts, you will get the same direction. That is the North Pole on the left hand side. So it depends upon you. You just need to place your finger with the reference of electric current, right?
Right, sir.
So just try to solve or just try to find out the direction by using pen or pencil as a conductor and just place your hand over it in the direction of electric current. Because in this specific direction, you know that current is moving in upward direction from front of the coil. So just take simple step, place your hand on the conductor in front of it and just curl your finger in the manner that current is moving in upward direction. So you automatically get the simple concept that we place our palm on the screen and just try to curl those fingers so you will get the direction that current is moving in upward direction in front of coil. And if current is moving downward in front of coil, just we consider in this example, so we need to place our hand or our palm backside of the conductor and curl your fingers towards your side. So that will give you the direction of electric current. So in this specific condition, we conclude that this thumb represents you the direction of North Pole and the direction of fingers gives you the concept of moving electric current through a coil. So we need to place our hand over conductor, and the very first idea is that you need to curl fingers in the direction of electric current. And then second concept, the thumb will give you the direction of North Pole. Any question, any confusion in this
No, sir,
diagram?
all clear.
Okay, so take it very simple. Just first find out the direction of current, place your fingers in that, and you will easily get your answer. We also consider the diagram that in diagram hand is from placed from the back of the coil, right? Because they want to show that how we need actually find out. But if you place your hand in front of it, so direction of electric current will not visible, right? So that's why they use the hand from the back side of the conductor. But if you place in front of conductor, you are also getting the same direction. So don't get confused that either we need to place in back of the conductor or front of conductor. So just take it simple, place it fingers in the direction of current and you will easily get the direction of magnetic field in right hand rule when we are talking about two quantities only. So thumb basically represents the North Pole. So very simple concept. And this whole concept is known as Fleming's right hand rule. So we are talking about Fleming's left right hand rule. So no confusion in Fleming's right hand rule, right?
Yes, sir, no more.
Okay. Okay, so continue with the left hand rule. So basically we use left hand rule for the third concept in our electromagnetism, that is for the direction of the force or the direction of motion of the conductor. So let's suppose we consider new concept over here, and that concept is specific when we are working with magnetic field and the direction of electric current, right?
Right, sir.
So let's suppose we are having a magnetic field now, because in previous concept, to compare all these concepts which we are talking about, in previous we are not having magnetic field, right? We are just having electric current or and conductor. So we are not having pure magnetic field over there. So that is the difference from first concept in and this concept. So let's try to find out what is different in this concept. So let's suppose we are talking about a current carrying conductor in a magnetic field. So let's suppose we are talking about a conductor placed in a magnetic field, and what will happen next? So first we need a magnetic field over here. So let's try to continue with the magnetic field. So there is a north pole on left hand side, and there is a south pole on right hand side. And magnetic field will always flow from north to south. We already know about this concept. And the same conductor is placed in the center. So we are having a conductor. A straight conductor is placed in a magnetic field and current is moving in upward direction initially, right? Okay. So now we have two quantities. One is of magnetic field, which is moving from north to south like this. So this blue line gives you the concept of the magnetic field that is moving from north to south. And this white line already giving you the direction of electric current through the conductor, right? So now we use our three fingers, but rule will also change. Now we need to use a left hand rule over there. So basically, we are going to find the direction of force, because we already know the direction of electric current. We already know the direction of magnetic field. So basically, the purpose of using this whole setup is that we will get third quantity that we use in a practical application of electric motor and some other movement. So we are getting third quantity, which is the quantity of force, right? To find the direction of force. Because we already know the all concepts, we are just going to revise all the quantities, that how to find the quantity. So in this particular case, when a current carrying conductor is placed in a magnetic field, so it will get a force, or force is going to be applied on the conductor in some specific direction, right? So we need to find out that in which direction this force is going to be act. So for that purpose, now we need to use a left hand rule. So how to use that left hand rule? So in left hand rule, we know that first let's talk about the thumb. So basically the thumb gives you the direction of
Force?
Yes. The thumb gave us the direction of force. And if we talk about the second quantity, which is the first finger,
The current?
current or magnetic field.
A magnetic field.
Yes. So you just need to remember this concept or this difference between first and second finger because mostly we got confused in that. So the first finger gives you the direction of magnetic field and the second finger will give you the direction of electric current, field and current. So when you are going to find out the direction of force, so just take it simple and start first from the magnetic field. So first we need to identify the direction of magnetic field. So it means that we need to place our first finger in the direction of magnetic field. So by using your left hand rule, in this particular condition, first place your hand just like palm is facing your side, right? And just open the first finger. So first finger will be in this direction, right? This is our first,
Yes.
this is pointing in the direction of magnetic field because we know that magnetic field is moving from left to right. So we just open our first finger and that will indicating towards our right hand side. Now let's consider the second finger and second finger will give you the direction of electric current. And one more important thing when we are talking about all these three quantities, so these all three quantities are mutually perpendicular to each other. Mutually perpendicular means we need to place fingers in such a manner that the angle between first and second finger, the angle between the thumb and first finger, the angle between the thumb and the second finger will always equal to 90 degrees. That is perpendicular. So that will clear another confusion that how to place finger, how do we know that in which angle we need to place. So that becomes clear. We need to place perpendicular, mutually perpendicular with each other, right? So let's suppose if you place our first finger towards right hand side, so what will be the direction of second finger? You need to now rotate your hand. Just place, now our two fingers are making L shape, right? Because both are perpendicular. One is, let's suppose, pointing in downward direction and second is pointing towards right hand side. So our both fingers are making L type shape because there is a 90-degree angle difference between them. So now you just need to rotate your hand in upward direction like this. That second finger will point in upward direction because current is moving in upward direction. So that is on y-axis. So we need to place like that. That current will or your second finger is pointing in upward direction. So now you need to rotate your hand like this. That the back side of your hand is facing towards you, right? Now palm is facing towards in front of you, or let's suppose towards the screen or towards the wall, which is in your front side, right?
You're right, sir.
And which what is the direction of force you are getting in this concept?
Downwards?
Downwards. Basically, that downward means into the page, right? Because magnetic field is on x-axis. This field is on x-axis because we know that all are mutually perpendicular, so it will divide equally in all three directions. And our second finger will be in upward direction.
So y-axis?
Actually, y-axis we are using for electric current because on screen we usually draw two axes, x and y. Z-axis cannot be drawn easily on the screen. So this second finger basically represents the direction of electric current which is on y-axis. So that downward thumb direction basically represents you. Let's suppose if your tablet is on your lap, so in that specific condition, thumb is pointing towards the screen or thumb is pointing towards the ground, right? So that direction basically represents that it is going into the page. So this is actually y-axis. And let's suppose if we try to consider with the help of a picture of left hand rule. So let me share the picture also. Okay, so there are multiple possibilities there that how we are going to place our magnetic field and how we are going to place conductor in the magnetic field. So multiple options are there, but the orientation for the left hand rule will always remain same, right? Let's suppose if you consider this picture where I am making star. So this is the correct position for left hand rule. All three fingers are mutually perpendicular. This is perpendicular with this, and this is perpendicular with this, and it is also perpendicular with this, right? So all three fingers are mutually perpendicular. And the second point you remember that first finger represents you the direction of field, the second finger represents you the direction of current, and thumb will represent you the direction of force. So all three are mutually perpendicular. Now you need to do just place your hand like this, which is on which is mentioned in this diagram, and just rotate your hand with the orientation of magnetic field and electric current, right? Just
Yes.
consider in our situation that we place first finger in magnetic field. So just open all three fingers. It means two fingers and one thumb, and just rotate your hand to align your hand with the direction of magnetic and electric field in the diagram, right?
Right, sir.
So any other confusion in this?
No, sir, it's very clear now.
Okay, so just place your three fingers. It means two fingers and one thumb in the orientation perpendicular to each other. And we just need to rotate our hand like to align with the orientation, right?
Yes.
So that is the concept. We don't need to open and close our finger again and again. So that is the simple concept of left hand rule when we are working with magnetic field and electric current.
No, right, sir.
Okay, so this is our left hand rule. And in this left hand rule, we will get the concept that how to place our left hand and what we are getting from left hand, right? So I think there is no more confusion in left hand rule.
Yes, sir.
Okay, further we need to discuss about the DC motor and AC generator. So we will continue with that revision also in our class. So in tomorrow class, we will try to solve some questions related from past papers, and time to time we also revise those concepts, right?
Right, sir.